Welcome to our presentation of our paper, the evaluation of video masked autoencoders performance and uncertainty estimations for driver action and intention recognition. Our presentation will briefly cover motivation of why we pursue this work, terminology of driving actions and intentions, the basic overview of the concept of self-supervised pre-training, an outline of our data sets, experiments that are moved, followed by results and the discussion and conclusion. So, driver intention recognition and action recognition are part of advanced driver assistance systems with the goal of reducing traffic conflicts. Reducing traffic conflicts is still relevant because we have a lot of human drivers on the road, and traffic deaths are still ranked among the top 20 death causes worldwide today. On top of that, nobody has yet tested the video masked autoencoders for a driver action or intention recognition setting, according to our knowledge, and especially relevant for applying AI-based systems in a high-risk scenario where every incorrect decision could potentially lead to harming a human being, is making sure that the system is able to express how certain it is about made predictions. These uncertainties could help refraining the model from predicting in scenarios where it's unable to make a confident prediction, and also support spotting where the model is incapable to improve it. Moving on to the terminology of what are driving actions and intentions. This is a bit of an nitty-gritty depiction of what it is. But suppose you are in a car over here and you want to overtake the car ahead. Then to do that, before you start to do anything, you need to form an intention, basically what you aspire to do. That's before you have done anything. To achieve that goal, you need to perform a sequence of actions, which we can observe. For example, looking over your shoulder, turn on the blinkers or move to the left. And together, these actions are denoted as the plan. So the difference between a goal and an intention is that a goal can be recognized after the first action has been started, initiated, whereas we really think of intentions as something before the first action of the plan has started, because you don't have to act upon an intention, but you can or you aspire to do so. Actions are the only things that we can observe, and that's basically what we rely on. Moving on to self-supervised pre-training as a method to train our networks. So basically, the paper of Chen et al. 2022 showed that using self-supervised pre-training actually enabled image classification models to improve. So what's the concept? For example, look at the image here. It's basically masked in a lot of places. Then we have an encoder learning that representation. Decoder is padded again, and then it tries to reconstruct the original target image based on the padded example it's given. And as you can see on the right side here, on unseen images, they're quite capable of reproducing an image based on a very small portion of the actual image. So basically what the network does here is it learns a representation based on a very sparse example it gets. And that actually allows for better representations, more robust, and to efficiently learn. So in a classification task, one would remove the decoder and just include a classifier, and that actually helps speeding up in performance. So similarly, Tong et al. have proposed something for videos. The problem only with videos is that, for example, if you look at a regular video here, the pixels of the sky are commonly the same. So therefore, they introduced tube masking. So any kind of patch of the image they mask throughout the entire image. Based on that, they have multiple tubes left with the same spots, which are fed into an autoencoder. Same principle as the other one is trying to reconstruct, in this case, the video. And that's actually it. It's basically reconstructing the video based on these patched, the masked input sequences, which yeah, allows for learning better representations. Moving on. The datasets for our experiments that we've used are the brain for cars, which you see on top, which includes both a in-cabin video stream synchronized with an external video stream, and the Honda Research Institute driving dataset. This one includes multiple scenarios, basically action recognition, where we aim to recognize what the driver of the ego vehicle currently is doing. Things as intersection passing, left turns, right turns. But this one, we only, for this dataset, from this dataset, we only use the exterior data, the camera data. So what did we do? Basically, we constructed an architecture where we, for each of the video streams, if they're available, depending on the dataset, use a pre-trained masked autoencoder. Previous studies also used pre-trained networks, commonly on the kinetics dataset. So that's actually a common way to ensure that we can learn something. That's also due to the size of the driving datasets with action labels, so that they're normally quite sparse. So then the resolution is commonly to use a dataset of pre-trained model and fine-tune from there. In order to fuse both data sets of both modalities, we use an attention fusion mechanism to decide itself what is relevant for the recognition task. And the recognition tasks in our scenarios are driver intention and action recognition. For sampling, we took the same approach as Rom et al. They wrote a paper about driver intention recognition, where they, to ensure that they sample from multiple a segment from a video, they divide the video in multiple segments, and from each segment they continuously sample the video frames. So we do the same during the training, and during testing we just use a uniform sampling of the frames. The results of the driver action recognition show actually that based on our approach, we outperform all previous methods that perform offline driver action recognition, so based on the short videos only, except for the U-turn, but on all other classes we aim to improve, and quite a significant improvement for the overall mean average precision performance. Yeah. For the intention recognition results, we see that based on the in-cabin data, we can't really say that we improve compared to, for example, MAE et al. But what we can say is that for the external data, we have quite a significant improvement, and if we fuse the data streams together, we also see that we improve quite a bit. Interestingly, the fusion method we applied here was an intermediate attention fusion mechanism, whereas we see that the concatenation almost, or it's quite indistinguishable whether it's better or not. But the late averaging approach, which was, for example, also used by Rom and Gebert, didn't yield the same performance. So there was also quite some improvement there based on the fusion mechanism. Then if we look at the capabilities of these methods to produce uncertainty estimations, what we did is we either set up the last layer of the networks to be where there we replaced the network weights with distributions. So we applied Bayes-by-Backprop, or we applied Monte-Carlo dropout, which basically means that during test time we also drop the network weights, which gives us, after a Monte-Carlo sampling, a predictive distribution. What the bars here show is that for the correct predictions, the methods produce a lower predictive entropy, average predictive entropy, for both models actually. And this tells us that it can distinguish, or it significantly produces lower uncertainty estimates for correctly predicted test instances compared to incorrectly predicted test instances. And this is a nice property of these methods, because this allows you to understand when the model is too uncertain to make a prediction. It doesn't tell you anything about what to do then, but that's of course not within the scope of this experiment. So in conclusion, we managed to outperform the previous state-of-the-art methods for both driver action and intention recognition without manually crafting any other kind of features. The problem only is for an end-to-end visual approach that it's a cold cognition approach, which means that you try to learn reasoning based on, or that you assume that the method will learn to reason implicitly, but you cannot extract explicitly what it's doing. The uncertainty estimation showed that the Monte-Carlo dropout and the Bayes-by-Backprop approaches were capable of distinguishing and producing higher uncertainty estimates for incorrectly produced test instances. And lastly, another important topic to remember is that for the uncertainty estimations, the Monte-Carlo sampling approach is probably not sufficient, or is probably too computationally expensive. If you, for example, need to perform 25 predictions for a single instance, that's quite costly for something like a video model. That's our presentation for our evaluation of video Masked Autoencoders performance and uncertainty estimations for driver intention and action recognition. Hope you enjoyed it. Thank you very much.